Today we're going to talk about congruent triangles. That's right, same size, same shape, same triangles as yesterday, only now they're congruent. So let's go ahead and start off. We're going to have to backtrack a little bit and talk about congruent polygons in general before we can talk about triangles specifically. So, congruent polygons. You know, congruent means same size, same shape. Polygons, hopefully you guys remember polygons, or those multi-sided figures with the straight sides. So if we're talking about congruent polygons, specifically, we're going to talk about two polygons being congruent if and only if their corresponding sides and angles are congruent. So anytime we have two polygons that are congruent, we know their corresponding sides and angles have to be congruent. And if their corresponding angles and sides are congruent, then those polygons are congruent. So here's our two polygons we're going to deal with. We have on the left polygon rock, on the right polygon salt. Together, polygons rock and salt. As you see at the bottom there, it says that polygon rock is congruent to polygon salt. What does that mean to us? If rock is congruent to salt, then we're going to talk about the two little pieces, corresponding sides, corresponding angles. If you remember back, corresponding means in the same position, same relative position, something like that. So we know actually exactly what goes with what because of the way that this is all written out for us. So the order of the rock and the salt, because it's written in the same way. We know that R has to go with S, and we know that O goes with A, and C goes with L, and K goes with T, because they have to be in the same order. So we know that angle R and angle S are congruent. We know that angle O and angle A are congruent. C and L are congruent. And K and T are congruent. Same thing. We know that we have RK and ST are the same. RO and SA. OC and AL. CK and TL. We have our corresponding sides, we have our corresponding angles, and they're congruent and they match up. This applies to any polygons, triangles, squares, rectangles, parallelograms, pentagons, octagons, dodecagons, whichever kind of polygon you want. We are going to focus on triangles though tonight. So, to do that, we're going to intro this new big geometry thing, proofs. This is our first experience with proofs, guys. And I know if you talk to people who have taken geometry before, they've taken it recently, they're probably going to tell you something like, oh my God, proofs are the worst thing in geometry. If you talk to people who took it way back in the Stone Age like I did, they say, oh my God, proofs were everything we did in geometry. For you guys, proofs aren't going to be everything, but it is going to be part of it. They're not that scary. People kind of freak out by them because it's a step-by-step process, but if you can do a step-by-step process, you can do a proof. Let's start off with the basics of what they are. They have a couple of key components. The first one is we have a given statement and a proved statement. Given is just simply that. It's what you're given to start off with the problem. What do you know to start with? So anytime you have a proof, you're always going to have something to start with. That's your given. That's your start point. Okay? And prove, that's what you're trying to prove. That's your goal. That's where we're going. Prove is the goal. To go along with that starting point, starting information, and your goal, typically they'll give you a picture. If they don't, you're going to draw a picture. If they don't give you one, you're going to put one over there. And then we get this kind of chart thing. In geometry, we typically use what's called a two-column approach to proofs. So we have two columns here. On the left, you see it's got statements, and on the right, it's got reasons. And just simply what we're going to do is on the left, we're going to write something that we know, what you know, and on the right, we're going to put, why do you know that? Why do you know that? What do you know, and why do you know that? So on the left, it's what you know. On the right, it's why you know that. Let's do an example. Here we go, example proof. So we're given a couple of different things, 4 different things to be specific. So you see that segment AD bisects BE, BE bisects AD, AB is congruent to DE, and angle A is congruent to angle D. So you got lots of stuff given in this one. Typically, you don't get as much given information. You just 1 or 2 things. But this time, you got 4 different things to go on. We have our proof. We have our goal. We are trying to prove in this picture that triangle ABC is congruent to triangle DEC. We can't jump straight to that. We have to kind of walk step by step. How do we actually know that that's true? I can kind of look at them and say, yeah, they look like they might probably be. But we got to think about how we're going to prove that. Right now, these are congruent triangles. Congruent triangles, the only thing we've got in our toolbox for handling that is to find everything else on that picture. All the other corresponding parts are congruent to each other. So let's start off with the ones we know first off the bat. We know that AB is congruent to DE. It tells us right here. AB is congruent to DE. It's even written there for us. It's convenient. So all I have to do is put it down as a statement. We know that AB is congruent to DE. We know that that's a true statement because it's given to us. We know that's true. Given. Second statement. We also know that angle A is congruent to angle D. Also given. So we got 2 little parts already there. Don't even have to do anything for those. Those are just given to us. Like your teacher's like, oh yeah, here you go. I'll only give you the answer. You've already got 2 of them. And it's already marked in the picture. You see the nice little arc marks with the angle A and angle D? And the little tick marks on BA and DE? Yeah, we got already that stuff is marked congruent. So we get 2 pieces down. We just got to get the other 2 sides and the other 2 angles. So let's go back and look at what else we've been given. At the top, we've got AD bisect BE. All right, let's deal with that. AD bisects BE. And that was given. Alright, so what does that mean if AD is bisecting BE? Well, bisect means cut in half. So if AD is cutting BE in half, I should end up with 2 equal parts there. To me, it looks like it's going to be BC and CE. So let me go ahead and say that BC is congruent to CE. How do I know that? It wasn't really given to me. The bisecting was given to me. But I used that term. I said, well, I know bisect means cut in half, so I got those 2 equal parts. So what I'm going to say there on step 4, for my reason that I know those are congruent, is that it's just a definition. That's what it means to bisect. So definition of bisect. Definition of bisect. Got it. Alright. So we got that. We've got 1 more pair of sides to do. Let's go ahead and do those because that second given statement looks like it's probably going to give it to me. I'm going to write it down. I got BE. BE is congruent. No, not congruent. It bisects. BE bisects AD. AD. And that was given. BE bisects AD. So I know that was given. And just like I did before, bisect meant cut in half. So BE is cutting AD in half. So I should get 2 equal parts there on AD. That's going to be AC and CD. Notice how I put the different number of tick marks to show they're not congruent to the first ones necessarily, but they are congruent to each other. So now I'm just going to go ahead and say that. AC is congruent to CD. I'm going to skip to another page, get myself some more room to write here. I got AC is congruent to CD. Alright. And the reason there again, because that's that bisector. So because I knew what the word bisect meant, I could put that there. So I'm going to say definition of bisect. Definition of bisect. Alright, so AC is congruent to CD, and that's a definition of a bisector. So let me go ahead and mark these again. And I still got to get the other angles. So let's see what I know. I'm out of given stuff, so I got to kind of just pull it out of my hat, so to speak. So first, I know I got an intersection right there in the middle. I see vertical angles. I see a little bow tie there, Mr. Olivier's favorite kind of angles, the vertical angles right there at the middle. I got angle BCA. Angle BCA is congruent to angle DCE. I know that because Mr. Olivier told me about those vertical angle things. We just had a test over that stuff. Vertical angles. They're the ones that are across from each other at an intersection. They're non-adjacent. They're not next door to each other, but they are always congruent. So I'm just going to say number 7, vertical angles. Vertical angles. Here we go. So we got one last pair of angles to go. We've got that these angle A is congruent to angle D. We got the BCA is congruent to DCE. We're good so far. We got to get that third pair of angles. Wait a second. Third pair of angles? Just on yesterday's, we talked about the third angle theorem. Third angle theorem says that if we have two pairs congruent, the third pair's got to be congruent too. All right, angle B is congruent to angle E. Angle B congruent to angle E, and that was my third angle theorem. If you need a quick refresher on the third angle theorem, you might want to go back and check out yesterday's video. It was the very last thing we talked about there, the third angle theorem. If you didn't quite catch it because you cut me off too soon or your YouTube cut out or something like that, go back and give that a look-see so you can refresh your memory on the third angle theorem. So now we got it all. We've got all of our angles. All of our angles congruent, all of our sides congruent. I'm good to go. Last statement, triangle ABC congruent to triangle DEC. And I know that because all of my sides and all of my angles are congruent. All sides and angles congruent. Beautiful. Done. First proof out of the way. Smiley face. Great job, guys. Catch you tomorrow.